Hi everyone, thanks for coming to my presentation. My name is Hongyi Jiang. I'm a PhD student from the Department of Applied Math and Statistics at Johns Hopkins University. Today I'm going to talk about my research, split cuts in the plane. This is a joint work with my advisor, Professor Amitabh Basu, and Professor Michele Conforti and Professor Marco Di Suma. They are both from University of Padova. The results presented here are from our paper, Split Cuts in the Plane. First, let me introduce some definitions. A split set is a convex hull of two parallel hyperplanes, such that there is no integer points in its interior. The closure of its complement is called a split disjunction. A split cut to the polyhedron is an inequality that is valid to the intersection of the polyhedron and the split disjunction. We also say that the split cut was derived by the corresponding split set. The intersection of all the possible split cuts of a polyhedron is called its split closure. Based on these definitions, there are two questions remain long open, even in two-dimensional space. The first one is whether there exists a polynomial time pure cutting plane algorithm to solve pure integer linear programs when dimension is fixed. Such algorithm, if it exists, would be a nice complement to Lenstra's polynomial time algorithm. The second one is whether the number of facets, which is also called the complexity of a polyhedron split closure, is a polynomial when dimension is fixed. We study these two questions and get results in two-dimensional space. Let me firstly talk about a polynomial time cutting plane algorithm using split cuts. The goal of the algorithm is to find the optimal integer points in the objective direction C within a given polyhedron, which is also called realization. First, we solve LP in the objective direction C on the realization. If it returns unboundedness or infeasibility, then the algorithm will stop. Otherwise, it will check whether the LP solution V star is integral. If so, it will return V star as the final solution. Otherwise, it will take a simplicial cone derived by the facets of the polyhedron, such that its apex is V star. Then it will apply our split cut generation oracle to derive a split cut on the simplicial cone. This cut is also a split cut to the original polyhedron. After adding this cut, we get a smaller realization, and then we just go to step 1. We repeat this over and over again until it stops. It can be proved that the algorithm will take at most a polynomial time before it stops. Due to the time limit, I'm not going to introduce split cuts generation oracle and the proof here. They are included in our paper. I'm also very happy to talk about this after the presentation. Next, let me talk about the complexity of a polyhedron split closure in two-dimensional space. Given a polyhedron, its split closure is proved to be equal to the intersection of the split closures of all the simplicial cones derived by the facets of the polyhedron. Since there are at most polynomially many such kinds of simplicial cones, it is sufficient to prove that a simplicial cone split closure has polynomially many facets. Without loss of generality, we assume its apex is not integral, otherwise it is trivial. And here is its integer hull. We define the effective split cuts as the split cuts that can cut off apex from the simplicial cone. There are two types of effective split cuts. The first type of split cuts are derived by the split sets that do not intersect with the interior of the integer hull. In the case of simplicial cone, this is the equivalent to Quatermain-Montgomery cut. Since it has been proved that a simplicial cone's Quatermain-Montgomery cut closure has polynomially many facets, we only need to study the second type of effective split cuts, which are derived by the split sets intersecting with the interior of the integer hull. We take one facet of the integer hull, From now on, we only consider the split sets intersecting with the interior of the integer hole and this facet. We will prove the claim that all the split cuts derived by these split sets would be dominated by the intersection of at most two split cuts. This means that a simplicial cone's split closure has complexity no larger than the complexity of its quartal-Montgomery cut closure, plus twice of the complexity of its integer hole. Since a simplicial cone's integer has polynomially many facets, this will finish the proof. Next, let me show how to prove the claim. We take the facet defining line L1. The 2 points on L1 are integer points. Next, we take a lattice line parallel to L1, which is called L2, such that L2 does not intersect with the integer hole of the simplicial cone, and the convex of the union of L1 and L2 forms a split set. If L2 does not intersect with the simplicial cone, then all the split cuts derived by these split sets will be dominated by the cut derived by the convex of the union of L1 and L2, which is actually a quartal-Montgomery cut. This proves the claim in this case. Next, let's consider the case when L2 intersects with the simplicial cone. We firstly define union interval of a line as a convex of two adjacent integer points on the line. It can be proved that a split set interior can intersect with at most one union interval of a line. Similarly, we can define union interval on the facet. Let U2 denote the unique union interval of L2 intersecting with the simplicial cone. If a split set interior intersects with a union interval of L2 other than U2, then it can never produce an effective split cut. Therefore, we only need to study the split sets such that their interiors intersect with U2, just like this red split set. We also assume that this red split set's interior intersects with the union interval U1 of L1 on the facet. It can be shown that the split cut derived by this red split set will be dominated by the split cut derived by this purple split set, which contains U1 and U2. Therefore, we actually only need to consider those split sets containing U2 and the union interval of the facet. To finish the last step of the proof, we take the first union interval of the facet from left and from right. We call them as U3 and U4. We firstly take a split set containing U2 and U3 and derive its best split cut. Similarly, we take a split set containing U2 and U4 and derive its best split cut. After some calculations, it can be proved that this purple split cut can be dominated by the intersection of these two black split cuts. This means that all the split cuts derived by these split sets will be dominated by the intersection of these two black split cuts. And this finishes the proof. That's it. Thank you.